lesson, we looked at set builder notation, and if we should recap a little, we looked at how we can replace listed sets using notations in sets. Now what we're going to do today, our main emphasis today, is to take you through two concepts and show you also how set builder notation can be interwoven in those concepts. And those concepts are intersection and union of sets. Good. So we're going to see how we can show union and intersection of sets using set builder notation. Now, before we actually make use of set builder notation, the first thing we have to understand or remember, and let's go back to our short-term memory, is what is intersection and what is union. When you see those two words, what comes to your mind? And I'm going to ask Quincy. Quincy, tell me what comes to your mind when you hear the word intersection.
The joining of two sets.
The joining of two sets. Do you agree with him, Videli? No. Tell him what it should be.
What is common in both sets?
What is common in both sets. So if I should draw a Venn diagram, and I have set A, and I have set B, my universal set out there, I have 1 region, 2 region, 3 region, 4 region. And as Videli said, what they have in common. And which one of the 4 regions tells me what they have in common? The third region, or region 3. And this is the region that they share, what they have in common. So this is the region of intersection. So when you hear the word intersection, right away the thought of sharing should come to your mind. The two sets have to get something in common. And we move to union. America, what do you think union connotes? What meaning do you think it connotes?
When you a combination of 2 or more sets.
A combination of 2 or more sets. And when we combine them, what do we do with them, Damien? We combine them, or we put them all together. Thank you, Damien. So if we should have another Venn diagram, we have our sets A and B again, and we want to union A and B. When we're finished, A and B should become 1. So we're going to shade the union of A and B. And there we have A union B. Everything in A and B. Now, that's using a Venn diagram. Let us try determining the intersection and union of sets using number lines. Upper set of numbers, the set A, and our lower set, the set B. Now each dot is represented by any one of these whole numbers. So in the set A, what would be the elements? Call them?
5, 6, 7, 8, 9, 10.
In the set B, I would have
1, 2, 3, 4, 5, 6, 7.
Now we go back to intersection. If we say they intersect, when we say they intersect, we say they share, they have something in common. What does A and B have in common when we look according to this number line here? Kieran?
5, 6, and 7.
5, 6, and 7. So if we put a loop around here, we'll see what they have in common. So A intersect B is equal to 5, 6, and 7. Now we want to union them. If we're going to union them, where will we begin, Videli?
1.
And where will we end, Damien? We will end at 10. So we will have everything here. Now what you notice is that 5, 6, and 7 occurs in both A and B. Now when we're going to list our set A union B, we have 1, 2, 3, 4. So we write 5, 6, 7, 5, 6, 7.
No.
No. We don't write them twice. We only record them once. So I'm going to take 5, 6, and 7 off the second set, and I'm going to finish off with 8, 9, and 10. So here we have our diagrammatic representation. We use our number line, and we got 2 sets. Now we're going to take our 2 sets, A intersect B and A union B, and we're going to rewrite these using set builder notation. Now what you notice first is that we use representations to come up with these sets that we have here. Now that we have these and we know what the elements are, we're going to move from here to our set builder notation form. So the name of our set here is A intersect B. We know we must open with a curly bracket or a brace. And we know we must have the set of x's such that, and then we look at our elements and we ask ourselves, which group of numbers did we take these from? They can be whole numbers, and they can also be from natural numbers. And if we don't want to say whole or natural, we can also say
Real.
they're real. And before we get to real, they are also integers. And after integers, we can also say they are rational numbers. Very good. So you see how many options we have? Now we're going to limit our options to whether you want to use natural or whole. Good? Now let's go with the first one. We have 5, 6, and 7. We know that it is at 5 where we begin, and we don't go beyond 7. So we have x is greater than and equal to 5, lesser than and equal to 7. X is an element or member of the set of whole numbers, and we close. Now that was the first example that we wrote using set builder notation. Now you know that there are 3 other ways in which we can go about writing that. Okay? So you're going to quickly write any one of the other 3 for me. Here I've made use of the greater than and equal to, lesser than and equal to. Good, we'll take one. Yes, Miracle, would you like to volunteer yours?
X
Mhm.
is such that x is greater than 4 and lesser than 8.
Very good. And here you should have completed with, did you use whole or natural?
Whole.
X is an element or member of the set of whole numbers. Good. And when I looked around, I saw the other 2. Now let us try A union B. We begin at 1 and we end at 10. Try that one for me. Yes, Damien, let me. Mm-hmm.
X is such that
Mm-hmm.
X is less than,
Greater than.
greater than or equal to 1,
Mm-hmm.
and more than or equal to 10.
X is an element or member of
Whole number.
set of whole numbers. Good. So, X such that X is greater than and equal to 1. So we begin at 1. X is less than and equal to 10. So we end there. And where do we get our X's from? The set of whole numbers. So here, after going through what intersection and union connotes and seeing representations of their regions, identifying them or the elements on a number line, here we have taken the listed sets and represented them in set builder notation form. Okay? So in as much as we can just take a set and write it in this form, we can also union and intersect them and write the results also in set builder notation form. Any question? Good. Now let us say we have 3 sets, A, B, C, D, and E. B, we have B, D, and H. And C, we have D, E, F, and G. We have 3 sets. Now I want you to go ahead and list the elements of these sets to me. So I'm going to put the sets on the board. The first one, I want A intersect B. Go ahead quickly. List the elements of A intersect B. Finish? Kieran, what did you get for A intersect B?
B only.
B only? So we have in A, B, C, D, E. And in B, we have B, D, F, and H. What is it they have in common? Is it only B?
B and D.
B and D. B and D. So we have B and D. Second, I want you to now list B intersect A. Bilali, what did you get?
B and D.
We got B and D again. So it doesn't matter if we put A, if the A precedes the B or the B precedes the A. The answer that we have at the back or the result that we have is the same. So we can say the intersection of sets is commutative. That's one law. The intersection of sets obeys the commutative law. Now let's look at another one. Let's try A union B. Yes, Miracle? What did you get?
A,
Mm-hmm.
C,
Mm-hmm.
D, E, F, G.
Now let's union B and A. Try B union A for me and see if you arrive at the same set. Yes, Videli. I see you have an arrow from here pointing up there. So that tells me that whatever you have here is the same thing that's coming down here.
Yes.
Good. So we find that B union A also resulted in A, B, C, D, E, F, and H. And so here we can write that A intersect B is the same as B intersect A. And A union B is the same as B union A. So we can say now, the conclusion we can arrive at is that the intersection and union of sets are commutative. Good. Fifth one. I want you to try, look at it first. I would have A intersect B, that's one set. And then I'm going to intersect C. A intersect B is one set. And we had it here. Intersect that now with C. And see what you would get. D alone, D was the only element. Sixth one. You're going to take the set A and intersect it with B intersect C. We're going to take B intersect C, and then we're finished intersecting B and C. Then we're going to intersect it with A. Damien, what you got when you did that?
D.
You got D again. Now before we draw conclusions, let's continue. So we have 5, 6, 7. We want A union B union C. You take A and B, the union of it, and then union it with C. Quincy? A, B,
C,
C,
D,
mm-hmm,
E, F, G, H.
and H. And the last one, the eighth one would be A is union with B union C. Would you give me your response?
A,
Mm-hmm.
B, C, D, E, F, G, and H.
So you got the same thing like Quincy. Good. Now let's draw our conclusions. With 5 and 6, we had A intersect B intersect C, and we got D. And in 6, we got A intersect B intersect C, and again we got D. So the conclusion we can draw there is that A intersect B intersect C is equal to A intersect B intersect C. And when we look down in the final two, we see A union B union C is equal to A union B union C. Now in this case here, we say the intersection and union obeyed the commutative law. Which law you think they were obeying here? Begins with E. Associative law. Okay? In the order in which we grouped them didn't matter. We got the same answer, same result. So the first thing we found is that intersection and union of sets can be represented using set builder notation. Another thing we discovered is that Intersection and union of sets obey both the commutative and the associative laws. Good. So I have a question here which I want us to apply what we just learned. Now let's read through the question. The universal set U is defined as follows. So here we have the elements of U, and their whole numbers from 21 all the way to 28. So before they go on, it says A is a subset of U. And if A is a subset of U, means that we're taking A out of U. We can't have A being formed anywhere else. The elements of A will have to be taken out from here. And is described in set builder notation as A is equal to the set of x's such that x is a multiple of 3 and x is greater than or equal to 21, lesser than or equal to 28. Let's go ahead again. A is a subset of U and is described in set builder notation as A is equal to the set of x's such that x is a multiple of 3. So we're going to stop there and ask ourselves, what is a multiple? So we have got to know that first before we can proceed. What is a multiple of 3? Who would like to answer that for me? Nobody? Come on. What would be a multiple of 3 in this set? Give me a multiple of 3 from the set, from the universal set. 21. Why did you choose 21 and not 22?
Because we can divide it into 21 equally.
Because when 3 divides 21, there are no remainders. If we divide 22 by 3, it will go 7 times with a remainder of 1. So we're looking for a termination when our division is done. Good. So we're looking for all the numbers that 3 can divide without leaving a remainder that's found in here. Also, the numbers are from 21 to 28. Now let's find out what the question really is asking us. The first part says, list the members of set A. So we're listing now. Good. So here we have set A, and set A is made up of the set of multiples of 3 from 21 to 28. What is going to be the first element of this set? 21, followed by 24, then 27. What about 30? Can we include 30? Now let's look back at our universal set. It begins at 21 and it ends where?
28.
So even though 30 is a multiple of 3, we cannot include it because it's not in our universal set. So we close off. Here we have listed our set A and the elements are 21, 24, and 27. Yes, Miracle? You want to add something there? Second part of the question. It says, B is a subset of U and B is equal to 22, 24, 26, and 28. Now first, we were given the set in set builder notation form and we listed the elements. Here, we're given the elements and we want to rewrite the set B using set builder notation. So that's a challenge for you. Quickly, use the set B and rewrite using set builder notation. Now this question here was actually taken out of 2010 CSEC paper. So we're stretching our ability a little, right? Even though it's grade 9. Good. Now, if you look at how A was coined, you can also pull your answer out of A. Now, when you look at 22, 24, 26, and 28, which set of numbers do you think they fall into?
Even numbers.
Even numbers. Apart from even numbers, we can also call them multiples of 2. So we have options there again. Good. Fidelity, did you use multiples or did you use even numbers? Even numbers. So we write x such that x is an even number. And then we got to specify now where these even numbers are. And
X is more than 21.
x is greater than 21. X is lesser than
And equal to 28.
and equal to 28. And we close. So we know that these even numbers that we're talking about, they cannot be lesser than 22. And they cannot be greater than 28. Okay? Kieran, you there with us?
Yes, yes.
Good. So here we have looked at intersection and union of two sets. We can take the intersection and union of two sets and we can write them in set builder notation form after we have initially identified what their elements are. We can also have the set builder notation form and list the sets. And what we also found is that the intersection and union of sets obey two laws. And what are those laws? The commutative law and the associative law. Lesson 12. Sets, intersection, and union. In this lesson, we will use set builder notation to describe the intersection of two sets. We will also describe regions representing intersection and union on a Venn diagram. Here are some key points. The intersection of sets A and B is the set of elements common in both sets A and B. A intersect B is written as the union of sets A and B is all of the elements contained in A or B. A union B is written as given that the set A is equal to x such that x is greater than -4, lesser than 3, x is an element or member of a set of integers. The set B equals x such that x is greater than or equal to -2, lesser than 6, x is an element or member of the set of integers. We notice that A intersect B is equal to -2, -1, 0, 1, 2. A union B is equal to -3, -2, -1, 0, 1, 2, 3, 4, 5. Let us use set builder notation to give well-defined descriptions of A intersect B, which is equal to -2, -1, 0, 1, 2. X such that x is greater than or equal to -2, lesser than 2, x is an element or member of the set of integers. X such that x is greater than -3, lesser than 3, x is an element or member of a set of integers. X such that x is greater than or equal to -2, lesser than 3, x is an element or member of a set of x such that x is greater than -3, lesser than or equal to 2, x is an element or member of a set of integers. Let us use set builder notation to give well-defined descriptions of A union B, which is equal to -3, -2, -1, 0, 1, 2, 3, 4, 5. X such that x is greater than or equal to -3, lesser than or equal to 5, x is an element or member of a set of integers. X such that x is greater than -4, lesser than 6, x is an element or member of the set of integers. X such that x is greater than or equal to negative 3, lesser than 6. X is an element or member of the set of integers x such that x is greater than negative 4, lesser than or equal to 5. X is an element or member of the set of integers. The operations intersection and union obey certain laws. Compare and contrast addition and multiplication. Commutative law. A intersect B is equal to B intersect A. A union B is equal to B union A. A plus B is equal to B plus A. A multiplied by B is equal to B multiplied by A. Associative law. A intersect B intersect C is equal to A intersect B intersect C. A union B union C is equal to A union B union C. A plus B plus C is equal to A plus B plus C. A multiplied by B multiplied by C is equal to A multiplied by B multiplied by C. Let us examine the distributive law carefully. A intersect B union C is equal to A intersect B union A intersect C. A union B intersect C is equal to A union B intersect A union C. X is distributive over addition. A multiplied by B plus C is equal to A multiplied by B plus A multiplied by C. A plus B multiplied by C is not equal to A plus B multiplied by A plus C. Addition is not distributive over multiplication. Example 1. Given the set A is equal to 0, 1, 2, B equals 1, 2, 5, 6, and C equals 0, 2, 7, find A intersect B. Solution 1, 2. B, A intersect C. Solution 0, 2. C, B intersect C. Solution 2. D, A union B. Solution 0, 1, 2, 5, 6. E, A union C. Solution 0, 1, 2, 7. F, B union C. Solution 0, 1, 2, 5, 6, 7. G, A intersect B union C. 0, 1, 2. H, A intersect B union A intersect C. Solution 0, 1, 2. Example 2. X union Y is equal to A. A, B, C, D, E, F. B, A, B, C, D. C, E, F, D, B, C. Key, B. Summary. The intersection of sets A and B is the set of elements common in both sets A and B. A intersect B is written as the union of sets A and B is all of the elements contained in A or B. A union B is written as problem for today. Page 30, exercise 3C, questions 2, 4, and 6. Mathematics for Secondary Schools in Guyana, Book 3. Solution for the problems given in the last lesson. Pages 28 to 29, exercise 3B. Use the symbol is contains to make a true statement about each of the following pairs of sets. 2. C is equal to the set of natural numbers. D, the set of whole numbers. D contains C. 4. The set P is equal to X such that X is greater than and equal to negative 4, lesser than and equal to 4. The set Q is equal to X such that X is greater than 0, lesser than 3/4. P contains Q. 6. A is equal to the set of integers. B is equal to the set of rational numbers. The set B contains the set A. 8. The set A is equal to the set X such that X is greater than and equal to negative 2, lesser than 1. X is an element or member of the set of real numbers. Set B is equal to X such that X is greater than or equal to negative 2. X is an element or member of the set of real numbers. The set B contains the set A. Given that A is equal to 2, 4, 6, 8, the set B is equal to 1, 2, 3, 4, 5, 6, 7, 8. The set C is equal to 3 and 6. State whether each of the following is true or false. 10. B is a subset of C. False. 12. A contains C. False. 14. Given that number in P is equal to 6, determine the number of subsets of P. 2 to the 6th power equal to 6 to 4. 16. If number in the set A is equal to Q, write in terms of Q the number of subsets of A. 2 raised to the Q power. 18. If A and B are disjoint sets, is it true to say that B is a subset of A? Yes. 20. If B equals ABC, write down all the subsets of B. Empty set: A, B, C, AB, AC, BC, ABC. And do you like the concept of union? And always remember that when you union, what do?
We bring everything together.
You bring everything together. And Miracle, if everything there and there's some elements occur twice, do you put them back? You double them up in the set you're listing? No. Damien, which part of the lesson was your favorite part?
The part with intersection.
Part with intersection. Okay. Videli, what part did you like? Which part are you going to take back to 4 science?
The entire list.
The entire list. No, that's good.